Hello and welcome back to Homework Help for Math 2. Today we're going to be looking at Unit 5, Geometric Figures, Lesson 1, How do you know that? Start with the Ready section. It is said that a picture is worth 1,000 words. Mathematical symbols can be just as important when communicating about geometric diagrams. Decide which of the symbolic statements are correct based on what is given in the diagram. Justify your answers. So for number 1, we have two triangles, triangle ABC and FDE. And for each of these triangles, we are told the angle measurements in degrees for all three triangles. And it looks like angle A and angle F have equal measures. Angles B and D have equal measures, and angles C and E have equal measures. And we are not given any information about the side lengths of these triangles. So, for number 1, sorry, 1A. The first statement says the measure of angle ABC equals the measure of angle FDE. So we just got to make sure that we know which angles they are referring to here. So for angle ABC, if we trace this, if we trace the ABC, I'm going to start at A, I'm going to go to B, and then I'm going to go to C. It's going to look like this. Do that again. Okay. It's going to look like this. And then like that. And so the angle that is formed is going to be angle B. Then for FDE, again, we go from F to D, and then from D to E. So we're talking about angle D. And because this statement is dealing with the measurement of the angles, essentially what this is saying is it's saying 52.9 equals 52.9, which is a true statement because the measure of angle ABC is 52.9 degrees, and the measure of angle FDE is 52.9 degrees. And so for number 1A, this is correct. So this is a correct statement to make based on the picture as well as the mathematical symbols that are involved. And the reason is the diagram indicates both angles have equal measures. Specifically, that's 52.9 degrees. And it is appropriate to use an equal sign in this context. And again, the context here is that we're talking about the measurement of the angles. Part B. Part B says that the measure of angle ABC, so it's the same angle, is congruent to the measure of angle FDE. So, as a reminder, this symbol here means congruent. We'll be seeing that symbol a lot, so it's very important that we can recognize that. And this statement is, drum roll, incorrect. So this statement is incorrect, even though it's obviously very similar to A, right? And A was correct. These two statements look almost identical. However, this is incorrect because while the angles are congruent, right? So angle ABC is congruent to angle FDE because they have equal measures. So while the angles are congruent, it is not correct to use a congruent symbol to compare the measurements of the angles. An equal sign should be used instead. So as we saw with part A, when you're talking about the measurement of the angles, that's a number, right? Measurement is going to be some number. So here, that number happened to be 52.9. But the measurement of an angle is always going to be some number. And because it's a number, it means that you can use an equal sign to compare it. Congruent is used to basically compare two identical figures. That's why you could say that the angles are congruent, but not the measurement of the angles. The measurement of the angles are equal because it's a number. Part C. Part C says triangle ACB is congruent to triangle FED. So the order of the letters matters. I just wanted to double check that. So ACB and FED. Okay, so the order of the letters, quote unquote, would work here if we were trying to get this statement to work. The problem with C is that even though we know a decent amount about the angles in this picture, we know the measure of basically all 6 angles between the two triangles. We don't know anything about the side lengths. And we certainly cannot assume that this picture is drawn to scale. So even if it looks like the triangles are congruent, that is not sufficient. We're going to need some actual concrete information about the side lengths in order to make a statement like C. And again, we don't know anything about the side lengths, any individual side length. So for part C, our answer, the statement rather, is incorrect. So based on the information provided in this picture, we cannot make this statement. And the reason is that not enough information is provided to say that the two triangles are congruent. Now, the triangles are similar. If you have two triangles and all of the angle measurements are the same, it does mean that they are similar. So we could say triangle ACB is similar to triangle FED. But there's not enough information for us to say that they are congruent. And if you didn't mention that second sentence is extra. So if you didn't recognize that these are similar triangles, or if you didn't say it in your answer, it's not you don't have to say it here for C. I just wanted to kind of throw that in there, just in case anyone did in fact recognize that these are similar triangles. Part D. Triangle ACB is equal to triangle FED. Well, without even looking at my picture, I know this is incorrect. All right. So even if you were not given a picture here and you were just given this statement and you didn't really know anything about the triangles, this statement is not going to be correct because it is not appropriate or accurate to use an equal sign when comparing triangles. All right. So the whole idea the whole reason why we have a congruent symbol is to compare figures, and in this case, a triangle is a figure, to compare figures that are essentially identical, same size, same shape. So in this context, because we're talking about a triangle, you would not use an equal sign. If anything, you would use a congruent symbol. But as we saw in C, we also can't even use that with this picture because we don't have enough about we don't know enough about the triangles. All right. Last thing with part D, if if this was talking about some measurement of the triangle, so like for example the perimeter of the triangles, then that might be true, right? I mean, if we would, again, we would have to know the side lengths, but if all the side lengths were the same, then if we wanted to say that the perimeter of triangle ACB equals the perimeter of triangle FED, that's fine. Or area, that would also work. But the reason is because those are numbers, those are measurements, they're not figures. All right, next set of directions say, create a diagram based on the given symbolic statement. Be sure enough information is provided in the diagram to validate each statement. And the first assigned problem was number 4. 4 says that the measure of angle HAT is equal to 50 degrees. All right, so we need to draw an angle here. And it would be nice if it kind of looked like it was 50 degrees. So let's, in order to draw an angle here, I'm going to draw one ray, just like that. And then I'm going to draw a second ray. And again, it would be nice if it was kind of close to 50 degrees. 50 degrees is, a little bit more than 45, and 45 is half of a 90-degree angle. So if you figure, a 45-degree angle would sort of be going up, again, at about half of a right angle. 50 degrees is going to look just basically the same kind of angle. So it's going to look kind of like this, I would say. Yeah, something like that. And we're going to have to label some things here. So if we're talking about angle HAT, the part of this that we're kind of locked into, we're going to have 3 points here. So 1, 2, 3. And the piece that we're really locked into is that the letter at our vertex, right, where these two rays meet, this has to be A. All right. So that point there has to be A, has to be the middle point. My other 2 points can be, I can mix them up. It doesn't really matter. So I'll just put H up here, and I'll put T right there. If those were flipped, that's fine. And the angle that we're talking about is right there, because HAT, and that's 50 degrees. And I believe that should be sufficient. We could add arrows here if we want to. It's not strictly necessary. But that is a 50-degree, sorry. That is a 50-degree angle, HAT. I think we're good to go. Question 5. Question 5 says line ET is perpendicular to line LA. So it's going to be very important that we can recognize that this symbol means perpendicular. And it's not sufficient to simply know that it's perpendicular. We also have to know what perpendicular means. Perpendicular lines form a right angle. They intersect at a right angle, which is 90 degrees. So anytime you see this symbol, looks like a upside down capital T. That's the symbol for perpendicular. And again, perpendicular lines intersect at a right angle, which measures 90 degrees. So if I want to draw this, I'm going to draw a line. And this line, and it's a line, so I do technically need these arrows here. This line has 2 points on it. We'll say like there and there. And those 2 points are E and T. So that is line ET. Now that line ET intersects a second line LA at a 90-degree angle. So if I want to draw a 90-degree angle here, it's going to look something like that. And we'll add our line or our arrows. Okay. And this line also has 2 points on it. We'll say there and there. And that's L and A. And in order to indicate that these two lines are perpendicular, we have to include somewhere in this intersection, probably most commonly it would be in the top right, although technically it doesn't really matter where. Somewhere in this intersection, we need to have a box, just like that. And that box tells us that we have a 90-degree angle. And as long as you have that in one of the four, I guess, quadrants, right? So right now the box is in the top right quadrant. As long as you have it in one of the quadrants, that actually implies that all four of them are right angles. So you do not need to have it in every quadrant. Just one is sufficient. And the one that you put it in, I think, is largely irrelevant. So I just went with the top right. But anyway, so this diagram shows that line ET is perpendicular to line LA. Moving on to the set section, there are 4 ways of knowing that were discussed as part of today's lesson. They are knowing based on authority, examples, diagrams, and logical reasoning. Consider each of the scenarios below and identify which way of knowing best describes what is happening. So again, we've got authority, examples, diagrams, logical reasoning. And I think that this could be extended to outside of just a geometric or mathematical context and actually just to other areas of your life. So I would encourage you to think about, like, take anything that you know and just sort of ask yourself, well, how do I know that? And chances are I think it would fall into one of these 4 buckets, not just in, math, but in other areas as well. Number 7 says, every time I have drawn a ray with its endpoint on a line and measure the 2 angles formed with a protractor, they add up to 180 degrees. So, adjacent angles that form a straight line are supplementary. So, for number 7, the thing that we know here is this second sentence. Adjacent angles that form a straight line are supplementary. And then the first sentence sort of tells us how it was that we came to know that. And this is kind of a key phrase here. Every time. That's going to sort of help us figure out which bucket this falls into. But every time I do this, my angles add up to 180 degrees. So just to kind of ground what's happening here, this is saying that if I take a ray, we'll say something like this, and a ray is basically a piece of a line in that in one direction it continues on indefinitely like a line, but then on the other end it stops like a line segment. So it's like half line segment, half line. That's a ray. And it's saying that every time I draw a ray with its endpoint on a line, so I have a line, let's say I have a line that looks something like this. So something like that. It's saying that every time I do this and I measure the 2 angles that are formed, they add up to 180 degrees. So let's say we take this picture right here and we use our protractor to measure this. And let's say we measure the angle on the right to be, like, let's say 82 degrees, right? And then we measure the angle on the left, and the angle on the left is 98 degrees. And in this example, 98 plus 82 is 180 degrees. But it's saying every time I do this, they add up to 180 degrees, which means if I were to, let's say, draw a different ray, let's say I draw, say, this ray, just like that, and I, again, get out my protractor and I measure the angle on the right, and the angle on the right is, let's say, 13 degrees, and I measure the angle on the left, and my protractor says that the angle on the left is 167 degrees. And I take 167 and I add 13, and I again get 180. And saying that every single time I do this, I'm not going to keep doing it, but every single time I do this, they add up to 180 degrees. Well, it's not authority because I'm the one doing it. It's not logical reasoning because we're just sort of like playing around with this and we're noticing that every single time I do this, but we're not really reasoning as to why it's 180. We're just getting the result that it's 180. So it's either B or C, and in this context, B and C are kind of similar in a way because we're doing examples, and those examples are based on diagrams. However, it's not C because a diagram would be, it would be just one diagram that would apply to all of the examples. And as you saw on the left-hand margin, we've drawn two specific pictures. So C is used when you just have like one picture, and that one picture applies to all the scenarios. Whereas what we're doing is we're doing different scenarios every single time, and every single time this same result keeps happening. So what that means is our correct answer for 7 is B. We know this because it's based on a number of examples that we've done. We just did 2, but you could continue to do this, and every single time they're going to add up to 180 degrees. Question 8. 8 says, you know triangles that have a right angle are classified as right triangles. Okay. And you know the sides of a right triangle have a relationship described by the Pythagorean theorem. Okay. So you have concluded that when you have a triangle with a right angle, you can use the Pythagorean theorem to find missing sides. All right. So again, is that authority, examples, diagrams, or logical reasoning? In this context, the thing that we know is when you have a triangle with a right angle, you can use the Pythagorean theorem to find missing sides. How do we know that? Notice that in this example for 8, we sort of like build up to it, right? The first sentence says, you know triangles that have a right angle are classified as right triangles. Now, this question does not get into how do we know that, right? It does not get into how do we know that triangles that have a right angle are classified as right triangles. Chances are we just learned that in school at some point, right? Our teacher told us that when you have a triangle that has a right angle, the type of triangle that is a right triangle, right? So we quote unquote know that first sentence. Also, we know that the sides of a right triangle have a relationship described by the Pythagorean theorem. Again, this question does not get into how we know that. Chances are, and this might not be true, but chances are we were also told that in school, right? At some point, our math teacher said, all right, when you have a right triangle, there's a relationship between the sides. It's a very famous theorem called the Pythagorean theorem. Students can never pronounce it correctly. And that's what we're going to be using in class today. So question 8 is sort of building up to this idea that's highlighted about what you can use when you have a right triangle. And so because we are sort of using the red sentence and the green sentence to get the highlighted sentence, this is actually not authority. Even though it is quite likely that both the red and green sentences themselves did come from authority, right? Now, we don't know that for certain, right? And for different people, it might be different things. But again, there's a decent chance that the two underlined sentences came from some sort of an authority. However, we are the ones saying, all right, well, if we take those two things, and the next sort of logical step here is that when you have a triangle with a right angle, you can use the Pythagorean theorem. So that conclusion is not based on authority. Um, we're not really looking at specific examples here. We're just talking about triangles and angles and Pythagorean theorem. There's no mention here of a diagram that sort of proves that this is true. And so it turns out for 8, the correct answer is D. We know this based on our logical reasoning. It's almost like there's statement 1. Actually, you know what? I'll do it in the same color, right? So statement 1 was in red. Statement 2 was in green. And sort of like when you combine these two statements, it gives you the result that we now know. And so we sort of came up with it ourselves based on our own logical reasoning here for number 8. Question 9. I know supplementary means the angles add up to 180 degrees because my teacher from a few years ago just told me. All right? So we have this word that comes up in geometry a lot, talking about angles, supplementary. So definitely going to want to know what this word means. And it means that the two angles sum to 180 degrees, and my source for that information is my teacher from a couple years ago. Well, we do not know this from looking at a bunch of examples of angles that sum to 180. There were no diagrams involved in this problem, and we didn't really logically reason our way to this definition of supplementary. We know that this is true based on an authority, right? And in this context, the authority was my teacher from a few years ago, right? And we are sort of assuming, we are hoping that my authority both knows what they're talking about and is not lying to me. Now, hopefully, it's a teacher. Why I don't know why a teacher would intentionally lie. So hopefully, the teacher knows what they're talking about. But luckily, in this case, the teacher does know what they're talking about because supplementary does mean that the angles add up to 180 degrees. And this authority does not, in other contexts, the authority does not necessarily need to be a person, right? So sure, it could be a teacher or a parent or an older sibling, whatever. There's lots of people that can be authorities. But a textbook that just flat out says this. If a textbook says supplementary angles means the angles add up to 180 degrees, that is also an authority. So please don't make the mistake of thinking that the word authority here only refers to people. It's basically any time we know something is true because we were told it, and we sort of accept that thing is true. That's what it means to know something based on an authority. Next question was number 12. I know you can always turn a quadrilateral into two triangles because of the way they look. Just draw a picture of any quadrilateral and then connect opposite corners and you will have two triangles. It works because of the drawing. Try it. We're going to want to remember what a quadrilateral is, right? So just as a reminder, a quadrilateral is a four-sided polygon. And there's certain properties of polygons. They have straight edges. They are closed figures. What else is true about a polygon? Straight edges, closed figures. I think that might actually be it. But any four-sided figure with straight edges I believe should be a quadrilateral. So it's saying just draw a picture of any quadrilateral. All right, well, I'll just draw like a random quadrilateral, right? Because there's a lot of different kinds of quadrilaterals, but I very intentionally want to make my quadrilateral like not special in any real way. I just want to draw a quote unquote random quadrilateral. So let's draw something like, I don't know, like maybe that's side 1, then that's side 2, then that's side, we'll go, yeah, there. That's side 3. Am I going to be able to move that? Hopefully, okay, good, yes. And then this will be side 4. All right. I think that's random enough for our purposes. It almost looks like a trapezoid, but it's not because the bases are not parallel. They would intersect at some point. So, yeah, this is just a random quadrilateral. Nothing really special about it in any way. And it says connect opposite corners. All right, well, obviously we've got 4 corners to choose from. Right, so 1, 2, 3, 4. It's saying connect opposite corners and you will have 2 triangles. All right, well, if I connect, let's say, these 2 corners, like this, because these are opposite corners, what do I get? Well, I get this triangle, and I get this triangle. Yeah, so that works. And I could see that if I did the other 2 opposite corners, I would also get 2 triangles, right? So I could connect the other 2, but I mean this is sufficient. So it's almost authority. It's almost knowing on authority, but it's not, because this person, whoever's kind of talking to us here, is saying that like, well, they know it, but don't take my word for it. You do it, right? So if this person for number 12, if they were talking sort of at us and they were just saying, you know, a quadrilateral can be divided into 2 triangles, and we were like, okay, then that would be authority, right? But this picture is saying draw it and then see what happens. Also, let me skip B and C. We also know it's not D because we didn't really logically reason ourselves into this result, right? We can see the result, but we didn't really like think it through. We just sort of did it, and then we sort of noticed what happened. So there wasn't really a lot of logical reasoning happening here. So we've narrowed it down to B or C, either examples or diagrams. And I almost want to choose B here because we did technically draw an example of a quadrilateral here, but we really only did it with one. We did it just with one picture. Okay, we didn't draw like multiple quadrilaterals with like we didn't draw like a rectangle, then a rhombus, then a trapezoid, then a kite. We didn't do all of that. We just sort of drew a quote random quadrilateral and we looked at what happened. So this is actually not based on examples. Based on examples kind of requires there to be like just, okay, this thing keeps happening. It seems like it's true. It's like you're noticing a pattern. That's what knowing based on examples looks like. It's a pattern that comes from like recurring different examples. That's not what we did here. So what we did here was we did C, was we drew a diagram, and then based on that diagram, it certainly looks like any quadrilateral that we draw, if you connect opposite corners, you will get 2 triangles. So for 12, we know that that's true based on diagrams. Moving on to the Go section. If 2 angles share a vertex and together they make a straight angle, then the 2 angles are called a linear pair. And below are 3 examples of linear pairs. So we're going to want to remember what a linear pair is. So again, 2 angles share a vertex. So in the picture on the left, the vertex for each angle is right there, right? Let me just go ahead and do all of my vertices. Right. So for the angle on the left, it's right there, and for the angle on the right, it's right there. So in both examples, they share a vertex. Same thing with the one in the middle. So those two angles share a vertex, and these two angles also share a vertex. It's the same point. And the two angles, when you put them side by side like this, they make a straight angle. So that's a straight angle. That's a straight angle. That's a straight angle. Then they are called a linear pair. Okay. We can see here we've got examples of linear pairs in real life. Picture on the left, we got a lighthouse on an island. Notice that the sort of the where the land meets the water is my straight line, and then the lighthouse is kind of forms an angle with that ray, and so that would be an example of a linear pair. And then over there on the right, this is probably a picture. I'm guessing this is a picture from like San Francisco, and so the the perspective of this picture is interesting because it looks like the building is tilted, but chances are I'm assuming that the building is straight and that the street that we're on is tilted. So this is probably built into like the side of a hill here. Anyway, we can again see that in this case the road is the straight line, and then the edge of the building is the ray, and both of those angles share a vertex. I'll do that. So for the lighthouse, that's my vertex, and for the road, that's my vertex, and the two angles are next to each other and they form a straight line. Directions for 14 say, for two angles to be a linear pair, they must share a vertex on a side, and the sum of their measures must be 180 degrees. So they have to share a vertex on a side, and the sum of their measures must equal 180. Find the measure of the missing angle. So for question 14, we have a linear pair because I have two angles here and they share a vertex and they form a straight line. We need to figure out, all right, what's the measure of the angle on the left if these are a linear pair? All right, well, anytime I don't know something, it's always a good idea in this context to just like assign a variable to it. So we'll just say x. So this angle, this angle here, we'll say is a measure of x and is measured in degrees, so x degrees. And what we know about linear pairs tells us that if we take the angle on the left, which is again x degrees, and we add 60 degrees, we should get a straight angle. Now the measurement of a straight angle is 180 degrees. Okay? Just like the measure of a right angle is 90 degrees, the measure of a straight angle is 180 degrees. It's not a range like acute or obtuse, but rather just a specific number of 180. So solving this is relatively straightforward. I can subtract 60 degrees from both sides. And what I end up getting is that x degrees is 120 degrees. So therefore, x is 120. So our answer here for 14 is 120 degrees. Question 16. Question 16 is going to be very similar to 14. I know my angle on the left. I don't know my angle on the right, so we'll call that x. And again, these angles are being measured in degrees. As a little sneak peek here, you will eventually discover, if you don't know already, that there actually is another measurement for angles besides degrees. They're called radians, and you will see those later. But for now, it's safe to assume that all of the angle measurements that we're talking about are going to be in degrees. But just in the back of your mind, file it away. Eventually, you're going to discover these things called radians, and that is that. So with 16, I have a linear pair here. I have two angles. They share a vertex. They form a straight angle. And I know that with a linear pair, if I take my two angle measurements, so I have 90 on the left, and I have x on the right. I have x on the right. I know that the sum of these is going to equal 180. Subtract 90. Subtract 90. And I end up getting that x degrees. 180 minus 90 is 90. And so the measure of the angle on the right is also 90 degrees. Notice that 90 degrees is a right angle, which means if you were to put a box here, that would be accurate because a right angle measures 90 degrees, and we also discovered that the angle on the right is also a right angle of 90 degrees. Question 18 says, linear pairs could be defined as being supplementary angles because they always add up to 180 degrees. Well, that's true, right? Linear pairs are supplementary because the definition of supplementary angles is that it's two angles that sum to 180, and we just saw that linear pairs sum to 180. So question 18 is asking, are all supplementary angles linear pairs? All right, so we just gotta be careful here that we know what we're talking about here. There's a difference between saying are all linear pairs supplementary and are all supplementary angles linear pairs, right? The first sentence that I just said, are all linear pairs supplementary? That's what the first sentence is saying. The first sentence is saying that all linear pairs are supplementary because they add up to 180. But basically what this question is saying is the reverse true, right? Is it true that all supplementary angles are linear pairs? And in order for this to be true, it has to be true for every single example, which means if it's not true, all we really need to do is identify one way that this is not true, and then that's sufficient for this question. So if I think about the different ways that angles could be supplementary, sure, you could have linear pairs, right? So if I have a line and a ray, don't know why that didn't straighten out. Try it one more time. If I have a ray like that, right? So I know that the measure of this angle and the measure of that angle are going to sum to 180 because they're linear pairs. But I also know, so let me get rid of that picture. I also know that if I have an angle in space there, and let's say that this angle here is, we'll say it's, keep the numbers simple, we'll keep 60 degrees, right? And then if I have some other angle just like hanging out in space, like there, and let's say that that angle is, we measure it to be 120 degrees. Well, these two angles, if I sum them together, I'm going to get I'm going to get 180 degrees, right? And those two angles are not linear pairs. I'm going to say that again. The picture that I drew on the left here in the margin, those two angles are not linear pairs because in order to be linear pairs, they have to share a vertex. And they have to form a straight line. And the angle up top, well, the vertex is there. The angle on the bottom, the vertex is there. They are clearly not the same vertex. They're two different points, and they don't visually form a straight line. But they are supplementary because the angle measurements sum to 180 degrees. So what we can say here for number 18 is that question is, are all Are all supplementary linear? Are all supplementary angles linear pairs? All right, and the answer is no. All right, that is not true, and I always need to explain why that's true. No, and the reason is that supplementary angles do not need to share a vertex and form a straight line. Share a vertex and I guess and a side, and a side. They also form a straight line, but supplementary angles do not need to share a vertex and a side, as we just saw in the picture on the left. Next set of directions say, find the supplement of the given angle. Then draw the two angles as linear pairs. Label each angle with its measure. So for number 19, we are told that the measure of angle ABC is 72 degrees, and B will be the vertex. Well, even if we were not explicitly told that B will be the vertex, we still know that B is the vertex because B is the middle letter. Right? So whenever an angle is named using three letters, so in this case A, B, C, whenever that happens, the middle letter is the vertex because, again, you sort of trace the angle in the order that the letters are written. So you'd start at A, then go to B, then you'd go to C. And when you do that, B would be the vertex. So we're told that B is the vertex, but we kind of already knew that. So just wanted to make sure that we're on the same page there. So we can go ahead and draw this. And again, it's nice if our pictures could be at least somewhat to scale. It's not a huge deal, but it's just going to make our lives easier if, whenever possible, if the angles that we draw are sort of in the right ballpark. So 72 degrees, it's an acute angle, right? It's less than 90, but it's kind of like a larger acute angle. So even though it is in fact less than 90, it's not like a whole lot less. So if I'm going to draw a 72 degree angle, we'll draw it on the left. It's going to look something like, once again, one of these days I'm going to stop doing that. Okay. If I draw a 72 degree angle, it's going to look something like this on the left. We'll say that, just like that. All right. We can add our arrows if we want. I don't think it's strictly necessary. We are going to have to label some points here. So what matters is that B is the vertex for the reasons that we've already said. Right? So that point there is B. And we're kind of locked into that. As far as A and C are concerned, in the absence of any additional information, we don't have any additional information, it doesn't really matter where the A and the C go in terms of like which one's which, but one of them has to go essentially in that area, and one of them has to go in that area. One of them has to be on the line to the left of B, and one of them has to be on the ray. And again, it doesn't really matter which one's which, so we'll just go ahead and label A as being on the ray and C as being on the line. And again, we're told that this angle here is 72 degrees. And we are looking for the supplement. So the supplement is this angle here. And it says find the supplement. So we know that 72 degrees plus x degrees is going to give us 180 degrees. So if we subtract 72 degrees from both sides, we are left with x degrees being 100 and nope, not 180. We are left with it being 108 degrees. So instead of saying x now, we can say 108. And it doesn't tell us that we have to label the other angle. So the other angle would be AB something. Right? This part is not strictly necessary, but you would need a point over here, and maybe that point is like, let's say D. And so now the supplementary angle would be ABD, because that's the angle that's on the right. But anyway, our supplement is 108 degrees, and we have our picture there on the left.